Hello! In the previous video we talked about a general introduction into the SLIC project, as seen from a technological standpoint. And in this video we will continue with discussing the SLIC project, and we will look at the technology that we've used. We will look first at the general overview of public lighting technologies, and lastly we'll have a look at the result of the SLIC project. So generally, when we talk about lighting systems, we talk a lot about traditional public lighting systems, which are built up out of traditional lights, high pressure sodium, low pressure sodium, or metal halide lighting systems. One of the biggest problems we have with those traditional public lighting systems is that the light quality is really bad. So as you can see on the picture, we have two cars lit by a high pressure sodium light, and both cars appear to be black in this light, while in fact one of the cars is red and one of the cars is dark blue. So this illustrates the problem with traditional lighting systems, that they have a really poor light quality. Of course, we've seen in the past years that there's been a huge shift towards LED lighting, and the major benefit of that is of course that you can save a lot of energy by switching your traditional lighting system to LED lights. And next to the energy savings, the advantage is that you get a much better light quality as well. This is also illustrated in the figure. You see two different color cones. Well, actually the cones are the same, but the lighting used is different. On the left side you see the cone lit by high pressure sodium light, and on the right side you see it lit by an LED light. And you can see that the much higher light quality of LED enables you to see much more clearly what the real colors of the cone are. So next to those two advantages, energy savings and better light quality, LED has two more important advantages. So we've seen that the energy efficiency of LEDs is much higher than high pressure sodium. Downside to that is that the initial cost of LEDs is a little bit higher, but there are two big advantages that also come into play when you start to apply LED lights. One of them is that you can dim your lights to an arbitrary percentage of their maximum brightness, and the other one is that the switching time of LED lights is very fast, especially compared to high pressure sodium lights, where the switching time is on the order of minutes, where for LEDs you can turn them on and off instantaneously if you want to. So the last two properties in which LEDs really work better than traditional lighting systems also enable so-called smart applications. So when we talk about smart lighting systems, we are really talking about three different levels. We talk about transition to LED lighting, and the first level in the transition to LED lighting is simply LED replacement. So we take our old lighting system, we replace all the lights with LEDs, and we don't change anything else. This leads to a pretty significant energy consumption reduction and a higher light quality of your public lighting system. So that's already quite two very important benefits from LED replacement. If we go one level higher, we talk about static dimming. So not only do we have LED lights, but we're also able to dim them statically. And static means that we can employ time-based dimming control. So that basically means we have a fixed dimming scheme that tells us when the lights should go on or off at a certain percentage of their maximum brightness. When we go one step more advanced, we talk about dynamic dimming, and we also talk about smart lighting. So if you hear somebody talk about smart lighting, they really mean dynamic dimming lighting systems. So what does dynamic mean? It basically means that you can control your lights in a dynamic fashion based on all kinds of external data. That external data can be based on traffic, so how much motion do I see on my road, what is the traffic flow, what is the density of the traffic on the road. But it can also be environmental data. So think about weather data, light levels, is it very dark outside, cloudy, etc. But it can also be based on the temperature, and of course it can also be a combination of the data, so that you combine traffic data and environmental data to determine when your dynamic dimming system should enable your lights and at what brightness they should be on or off. So employing dynamic dimming or smart lighting brings a number of benefits. You get very much fine-grained control of your lighting system. You can exactly determine when the lights should be on and off at what percentage. and what conditions you apply to those settings. And that leads, of course, to a very high potential energy savings. You can also take into account different environmental factors that you couldn't take into account before. For instance, you can try to minimize light pollution or other things that affect wildlife. But there are also a number of drawbacks when employing smart lighting systems. Of course, the system becomes far more complex because you need to install a number of sensors. These sensors are expensive. They're often more costly than the lights they control. And their life expectancy is also lower than the lights, so they need to be replaced more often than the lights, and they are expensive to buy. It's very difficult, as we've seen in the SLIC project as well, to properly design such a smart lighting system. And even if it's designed properly, it's still not trivial to do a proper commissioning of such a system. And the last point, maybe the most important one, is that it's typically a case of diminishing returns. So you have to invest ever increasing amounts of money, and the returns you get from it, energy savings, cost reduction, they tend to decrease with increasing expenditure as well. So in this video we discussed lighting systems, and we talked a little bit about the technologies that accompany them. And in the next video we will go into the 7 different SLIC pilots, what technologies we used, and also the results of the SLIC project itself. Thank you.